I will be presenting a project that I have been doing in my internship with Simone, Tassos Frogas, and Florian. It's about exploring galactic black hole binaries with laser interferometer space antenna. And I'm a PhD student at Nicolaus Copernicus University in Poland. So I think it's not important to discuss the formation channels, but just because I'm having a slide, so there are isolated binary evolution channels and dynamical formation channels and other like AGN disk and population 3. But over here, for the sake of this presentation, I will be talking about isolated binary evolution, including common envelope, stable mass transfer, and chemically homogeneous evolution. And this includes basically stable mass transfer and where one starts from a relatively wide binary, where the most massive star evolves first and it becomes a supergiant. At this stage, it overfills its Roche lobe and loses its envelope via stable mass transfer. At the end of stable mass transfer phase, it becomes a stripped helium star that soon collapses into a first-bound black hole, whereas in the meantime, second black hole, second mass. In the meantime, the second star evolves off, and it also becomes a supergiant star, and then loses its envelope via Roche lobe overflow. That's why the first-born black hole is expected to be born with a negligible spin. Now, when the secondary star evolves off its main sequence, the whole process repeats itself in reverse, and with the secondary filling its Roche lobe, the mass ratio of the binary now changes. If the mass transfer is again stable, then we strip once again the hydrogen envelope of the binary from the helium star and soon collapses to form the second born black hole. In the stable, in the second mass transfer, the binary shrinks and both of the binaries are close enough to merge within the Hubble time. And also, I'm considering here a binary which is chemically homogeneously evolving, where both of the stars are chemically homogeneous and they are tidally locked with each other. And these two stars are rotationally locked, rotationally chemically homogeneously mixed and rotationally locked, and they don't evolve off as red supergiants. Rather, they collapses directly into the black hole, whereas both of the stars are highly rotating. They might have the periods of a few days or less, and their tides are highly synchronized, which includes strong rotational mixing in their stellar interiors, which leads to homogeneous mixing of the star. LIGO and Virgo have already detected tens of galactic and extragalactic black hole binaries, a few double neutron stars, black hole neutron star binaries. However, the network of ground-based detectors can only detect a small fraction of in-spiral, a few seconds just before their final merger. That means that these binaries have already have enough information about their entire evolution, and the space-based detectors can detect a much larger part of their early in spiral, but the horizon of the LISA is only limited to Milky Way galaxy and other nearby galaxies. So the statistical studies can help us distinguishing between the formation channels of these black hole, all of the compact binaries, whereas it can also reveal their true origin, and such systems are electromagnetically invisible, especially black hole binaries. So it is challenging to estimate these binary black holes with LISA. We would like to answer the questions like, have there been any merging black hole binaries in the Milky Way galaxy? And can we find any merging black hole binaries in our galaxy? And will the properties of these black hole binaries will enable us to distinguish between their formation channels? In the rest of my talk, I will be presenting the preliminary results of my ongoing project. The approach we follow here is binary population synthesis. We have used synthetic black hole binaries at different metallicities using Poseidon framework. Poseidon, among the other functionalities, combines the rapid binary evolution codes and cosmic in our case, and with the large grids of pre-calculated MESA binary evolution models that are generated with the MESA code. And these models have been calibrated to produce well the both rates and distribution of observed properties of black hole binaries detected by LIGO and Virgo detectors. Then these synthetic catalogs have to be convolved with the metallicity dependent star formation history that would be appropriate for the Milky Way galaxy and LISA selection effects in order to finally produce predictions of these black hole binaries. For our analysis, we use fire simulation from feedback relativistic environments, Fire 2 project, which provides a specially resolved information about the metallicity evolution of Milky Way type galaxies in their evolution. Here we plot 1D and 2D distribution that has been extracted from Milky Way simulation that then we convolve with the synthetic binary population of the black holes. What we see here in these histograms is that most of the stars are formed within 10 kiloparsecs with the metallicities above the solar metallicities, but with its significant tail at lower metallicities down to 1/100 solar metallicity. And finally, the star formation rate of Milky Way galaxy is roughly constant with the time. Let's find the answer to the first question by studying the merger time scales of binary black holes. What I'm showing here is the distribution of earlier times for binary black hole population of different metallicities. These are different colors for 3 different formation channels. In this dashed line represents the age of the universe, that is 13.8 gigayears. From these histograms, we can get that mean value of the merger times for each metallicity. From these histograms, we find that all the channels form the binary black holes within the Hubble time, but only for the metallicities for 1/10 solar metallicity. In the chemically homogeneous in common envelope channel, the binary black holes comes with a very short merger time scales, especially at the lowest metallicity, whereas for the stable mass transfer and chemically homogeneous evolution, the binary black holes merge at time scales that are typically of the order of few gigayears. This really coincides with our intuition because the stable mass transfer and chemically homogeneous evolution channels produce binary black holes at the larger orbital separations than the ones that are produced via common envelope channel. This is due to the lack of second unstable mass transfer that shrinks the orbit more significantly and as compared to the stable one does. Let's compare these with the metallicity dependent star formation history of the Milky Way galaxy. The heat map here shows the normalized star formation rate as a function of time and metallicity, whereas the red line and the associated error bars show the median metallicities and their spread of the newly formed stars as a function of time scales. For comparison, with the three black lines for each formation channel, we show the maximum metallicity at each of each formation channel. We can get most of the binary black holes that are merging today would have been born around in the first 4 to 6 gigayears of its lifetime, when star formation was happening at the low enough metallicities. And according to this figure, we can say that merging binary black hole systems can exist in the Milky Way. If we move to the next question, would it be possible to detect such merging black hole binaries with laser interferometer space antenna? As we have already said that LIGO and Virgo can only detect small fraction of the last stages of the gravitational wave in spiral of binary compact objects. It has recently been proposed that numerous LIGO and Virgo sources may also be detectable by LISA.
Rafia,
LISA
two
will
minutes
be able.
left.
Okay.
2 minutes left.
Right. Most of the black hole binaries, interestingly, that appears to be circular in the LIGO band, will be eccentric in the LISA band, depending on their initial formation channels. However, LISA will also be sensitive to the binary black holes that are too wide to merge within the human lifetime. Here I show signal to noise ratio of the equal mass binaries of 10 solar masses as a function of its merger time scales using LISA sensitivity, and the dashed line represent the detection threshold of the signal to noise ratio, that is 8. We plot it for different distances from 0.1 kiloparsec to 100 kiloparsec, and we can clearly see that, for example, a binary placed at 1 kiloparsec can have a merger time scale of 10 million years. It would still be detectable by LISA. This would correspond to present-day orbital period of about few hours. So if we will not be able to have any merging binary black hole in the galaxy, we might be able to see galactic binaries at different stages of their inspiral that might enable us to distinguish between their formation channels. Moving to the last question, would we be able to distinguish between these formation channels of these binary black holes with LISA detector? What I'm showing here is the distribution of observable properties of binary black holes, chip mass, chi effective, and mass ratio that would merge within the next 20 years, and thus would also be detectable from the ground-based detector. All these signals would be loud, with having signal to noise ratios of 10 to 100 signal as I just showed before in the previous slide. So there's really no need to calculate signal to noise ratio of each one of them. What we see here is two subchannels produced similar distributions except for the chip mass, where the stable mass transfer gives support for slightly higher masses. It is interesting to compare these predictions with those of the population of binary black holes for the whole universe. The primary difference here is metallicity dependent star formation history. Most striking difference is the lack of fast spinning black hole in the common envelope channel.
Rafia, it's time to wrap up.
Just give me a minute.
Yeah, please, quickly. Thank you.
Okay, so these are those metal poor stars that were formed fast spinning binary black holes. Of course, all these are purely theoretical interest, and the chance to observe binary black hole merging in the Milky Way in the next 20 years is almost negligible. But what one wants to see is the distribution of these properties of these binary black holes that would be detectable by laser interferometer space antenna. These are binary black holes with orbital periods of few hours, and we identify them by estimating signal to noise ratio. So here I'm leaving some concluding points that one can read, and because I'm running out of time, so maybe I can have some questions if there are any.
All right, let's thank Rafia. We have time for one or two questions or a couple of questions.
I have a question, but I don't want to take it over. Rafia, you showed up, thank you for you showed a plot at some point where you showed the delay time distributions for different channels at different metallicities. And I was just wondering what the weighing was for the histograms that you used there. Did you just run a simulation at every metallicity, and so it's not really weighted by how common these metallicities are, or?
These plots are I guess they are weighted by the KDEs from the fire simulation.
So this follows what the fire simulation would be? So I'm a little surprised that you get, the same amount of, or the comparable amount of systems at each metallicity for the common envelope channel, or for the other ones as well. So I'm just surprised. But you do say they're weighted.
I don't remember exactly because these were plotted long times ago, and because I lost my hard drives and a lot of things, so maybe I will look into it again.
Okay, thank you. There's a question.
One more.
Okay, I would just like to circle back to that plot that you showed the star formation rates as a function of metallicity. Yeah, apologies for the almost unrelated question. No, the one with the next slide. Yeah,
this
that one. Okay, that one. Yeah. Just, I don't know if it's an unrelated question or not, but where did you take the data for the star formation rate as a function of metallicity and time? Because yeah, it's something that I've been struggling to find everywhere for the Milky Way.
Okay, this has been taken by from a fire simulation. It's open source available on the website of Northwestern University.